Last we discussed was about the reactions of alkanes. Now, today we will focus more on the preparation part of alkanes. Okay, let's see. First one, alkanes can be prepared from alkenes and alkynes. That is, if you have an alkene, I can have certain reagents which will add one hydrogen here and here. That way, you can get an alkane. And even when you have an alkynes, the same logic will work. You can have two hydrogens being added like this and thus getting an alkene. Which are those reagents? See, typically hydrogen gas, when it get adsorbed on the surface of a metal like nickel, palladium, platinum, that is called Sabatier-Sandrens process. At relatively high temperature, you will get radicals of hydrogen which can connect onto alkenes and alkynes, thus giving an alkane part. Nickel, when you mix with aluminium, correct, and add it with a base NaOH, correct, it will also generate some amount of hydrogen which is adsorbed on the surface. We call it as Raney nickel. This way, this is how the Raney nickel is formed. And hydrogen with palladium which is been activated with carbon, which means surface is been added with a powdered carbon, that will increase the activity of the palladium. That means the reaction would happen even faster. Then we have platinum dioxide, which we call it as Adams catalyst. Then we have nickel boron, which we call it as P2 catalyst in H2 gas. All of these combined, I mean, all of this in any form, if you take it, they all will help in reducing alkenes to alkynes. In case if you have to follow, well, last one has one small bit of difference here. In the case of last one, what you would notice is alkynes, if you have, are, let's say, C triple bond CH thrice like this. Now this can convert into alkene. Sorry, it can convert into an alkene, but not towards alkene. Okay, that is the role of P2 catalyst. Anyways, coming to the mechanism, in case if you have a double bonded carbon like this, a double bonded carbon, and then you have hydrogens getting adsorbed on the surface, hydrogen gas, maybe, it has broken this bond, hydrogen bond has been broken. So this electrons can attack here, the hydrogen can attack here simultaneously, and that will give you a four-membered ring between these elements. You can see like this is the one, here there is an attack, here there is an attack, and there is a breaking of a double bond. So you will get what we call it as the four-membered cyclic transition state. And this makes hydrogens to add from the same direction. Okay. See, what I'm trying to say is double bond is planar, correct? A double bond is a planar surface like this. On this planar surface, both the hydrogens are adding from the bottom or from the top. Got it? When both the hydrogens add from the same direction, we call it as syn addition. We call it as syn addition. And thus we will have H and H getting added. This is how the product formation is observed. Okay, so you can see H2 is added from the same direction and you call it as syn addition. Now, I'm sure you must have recognized this reactant, which is in a cis form, because both the hydrogens here are on the same direction. So that means it is a cis form. On that cis form, you are adding deuterium to it. So when you add deuterium, what you would get here is two deuteriums getting added like this. like this. Okay, they will be on the same side, or they can be coming from the bottom, which means they can be inside like this. So should I count it as two products? Well, not exactly. Reason being, if you may have noticed here, there is a plane of symmetry running through it. Okay, although these two are chiral centers, there is a plane of symmetry that is running through it. Okay, and that makes it mesoform. Since it's a mesoform, one second, this is a mesoform, which means you will count this one and this one as the same molecule. So this is one and the same product because they are superimposable. Clear? Likewise, in case if at all we asked about an alkyne which is reacting with hydrogen with one equivalent, which means I take 1 mole of hydrogen gas which was observed on the nickel, and as it adds to this triple bond, since you know that it is a syn addition means it is adding from the same direction. So I will first get hydrogens added on the same side, which implies I get a cis molecule. Okay, a cis isomer is what I will get. On this cis isomer, if at all I add deuterium to it, got it? Actually, what happens here is if I write it in terms of a Fischer projection, you will see that there is methyl here and methyl here. These two are the methyls, by the way. And these two hydrogens will be on the left and deuteriums will be on the right. Again, you can see there is a plane of symmetry running through it. Hence, it is a mesoform. And only one product is to be uh, represented. Correct? This is the final product, what you have, the Fischer form. Let me explain this more in a stereochemistry point of view. See, if you recall, we've done this. When you have a three-dimensional molecule and you represent from a side angle, we call it as a sawhorse projection. And this is the sawhorse projection of eclipsed conformation. And this is the sawhorse projection of a staggered conformation. And usually when you have a sawhorse projection here, this is also an eclipsed form. This is also an eclipsed form. And when you watch it from the top, this is how you represent, and we call it as a Fischer projection. I'm sure you guys could recall that. Now, if in the Fischer projection, mind you everybody, if in the Fischer projection there are two chiral centers, but then there is a plane of symmetry, wherein, remember that any two unique groups, like OH is a unique functional group here, these two groups are on the same direction, same side in the Fischer projection. When they are on the same side on the Fischer projection, we call it as erythrokind. What do we call it? Erythrokind. And if they are on the opposite direction on the Fischer projection, we call it as threokind. Okay, remember these words, we'll be using this a lot of times. Erythro and threo. Now notice this, everybody. When you had a cis molecule, correct? Hydrogen was here, methyl was here, methyl is here, hydrogen here. These are all on the same plane like this. Now, the minute a deuterium is coming from one particular end, correct? This pi bond is lost and this sp2 carbon has now converted into an sp3 carbon. Hence, what happens? You will get an eclipsed form where methyl will be on the similar direction and hydrogen will be on the same direction, and deuterium are adding from the same direction. Hence, here we will get a code here. It's important, formulation that you need to remember it directly. That when you take a cis molecule and make a syn addition, you will always end up with erythro as the product. So you can see this is the product which we got. While if you had a trans molecule here, see, I had methyl, hydrogen, hydrogen, methyl, deuterium, deuterium getting added. And it is a syn addition only again. And as soon as you add a syn addition here, you will get like this. Deuterium, deuterium will add from the same direction, hydrogen here. But methyl and this methyl will be up and down. And as you rotate it by 180 degrees, now methyl and methyl will come on the same direction. But because you rotate it, now deuterium, deuterium appears on the opposite direction on the Fisher projection. That does not mean there is an opposite addition. It is still an syn addition. But while representing the Fisher projection, where I have to represent both the methyls above and below vertical line, in that sense, you will see deuterium and deuterium will be on the opposite direction. Got it? So both these deuteriums are opposite in direction. Here also deuteriums are opposite in direction. Unlike in erythro, I can't get two products. What I'm trying to say, please listen to it carefully. That is, in case if I write methyl, methyl, you might ask, sir, deuterium, deuterium can add from this end also. Agreed. But since it is a mesoform, in this particular example, it is a mesoform. Why? Because there is a plane of symmetry that is passing through it. Because of its meso nature, these two compounds are one and the same. They're identical because meso compounds are superimposable. But when deuterium added and you got a trio product, here these two deuteriums and these two deuteriums are not on the same direction. Hence, if I get a 50% dextro, then I would get a 50% levo. That means I will get 50% of one enantiomer and 50% of the other enantiomer. Chances are 50-50%. And when you get 50% of dextro and 50% of levo, the solution of these two mixtures would be optically inactive. Optically inactive solution. And if you may recall, an optically inactive solution is called as racemic mixture. Okay. An enantiomeric mixture, which is 50-50%, will be optically inactive and it is called as racemic mixture. So in the trio kind, you'll get 50-50% of dextro and levo. Now, do we have to always imagine so much? Not exactly. You just need to remember these terms. That's it. See, here, when there is an addition happening, this is about addition formulas. This is about elimination formulas. Whenever you perform an addition reaction in organic compounds, and if you started with a cis molecule, you made a syn addition, you will end up getting erythro as a product. If you take a trans molecule, make a syn addition, you will end up getting trio product. If you have a cis molecule, make an anti addition. Anti means hydrogens or any groups that are adding from the opposite direction, not from the same direction of a double bond. Then you will get a trio product. Then if you have trans molecule making an anti addition, you will get erythro product. Elimination will also follow exactly the same coding, but in the reverse direction. That's it. Suppose I already have an erythro product, erythro reactant this time, and I'm making a syn elimination. That means I'm trying to remove the hydrogen, remove the molecules out of it. You will end up getting cis. If you have a trio and you make a syn elimination, you will get trans molecule. If you have a trio reactant, make an anti-elimination, you will get cis as a product. If you have erythro, make an anti-elimination, you will get trans as the product. Now, this is something which you will have to remember all the time so that it becomes easier. You don't have to draw all the structures all the time. You can directly check out what is the nature of the reagent, whether it will go for cis, syn addition or an anti-addition. Based on that, you can figure out what is the product. Okay. Usually, I would always recommend to remember it like this. CSE, computer science department. Okay, or computer science engineering. Correct. You can remember it this way, that you are expected to do computer science engineering by taking a test, TST test, and thereafter you can attempt CAT exam. Okay, so that you can eat well. Got it? You can remember it like this. EAT. It doesn't matter whether you remember as TAE or EAT. Correct? Because it works both in addition side as well as elimination side. Clear, everybody? Please make sure that you mug up this formula at any cost, because just by watching the reactant you are supposed to identify the products, write the Fisher projections based on that. Okay, so let me repeat it the one more time. Just check it out. If you have a cis molecule, make a syn addition, you will end up getting erythro. Erythro means on a Fisher projection the added group should be on the same side. Trio means on the Fisher projection added group should be on the opposite side. Okay, so trans, when you make a syn addition, you will get trio. Cis, when you make an anti addition, you will get trio. Trans, when you make an anti addition, you will get erythro. Let us put this into perspective here. Correct. Suppose in this case I have a methyl here. You don't have to disturb that. But you know that on a double bond, you will already have two hydrogens here like this, which is a cis form. This is a cis form. And when you make a deuterium to get added, you know that these hydrogens, if they are coming out of the plane, then both the deuteriums must have been added inside the plane like this. Or I can do the reverse way also. That means keeping the hydrogen's deuterium at a different position here like this. I can say that deuteriums are added here and hydrogens are present here like this. Okay, 1 second. All right. This is the way additions can happen. Everybody clear? Now, have you noticed what is the relationship between these two products, P1 and P2? Are they mirror images? Well, not exactly. If you figure it out, there are three chiral centers, 1, 2, and 3. Here also there are three chiral centers. Are they superimposable? Not exactly. Are they mirror images? Not exactly. They are non-mirror images, non-superimposable, but yet they are stereo isomers of each other. What do we call them? Diastereomers. So hence P1 and P2 are pair of diastereomers. Pair of diastereomers. And remember, everybody, diastereomers not necessarily have to be 50-50 percentage. Only when you get enantiomeric forms, then only you will get 50-50 percentage. Otherwise, diastereomers always end up having something like 60-40 or 70-30, like that. It will never be 50-50 percentage. Hence, will the solution be optically active or inactive? Of course, there will be some amount of racemization happening, but you will still have a small composition left by which solution will remain optically active. So it will be optically active solution. The first question is clear, everybody? So catalytic hydrogenation, everybody, is a syn addition. When you make a syn addition on a cis molecule or a trans molecule, you will end up getting various products. They could be called as erythrokind or threokind. In this case, because the groups are on the same side, you call it as an erythrokyne. Now notice this is a trans molecule, and here there is ethyl, which is already fixed configuration. This ethyl is also fixed configuration. So when I write the product in a three-dimensional fashion, I'm writing the product. So I will write the same ethyl here. I can say that both the deuteriums getting added on the same direction like this. Okay, one second. Like this, they both are adding on the same direction. This is one product I can expect, or I can say both the deuteriums are adding such a way they are inside like this, because I need to showcase that there is a syn addition in both of them. So these two are the products. Again, these three are chiral centers, but they are not exactly mirror images. So again, what are these two? These are pair of diastereomers. Pair of diastereomers. Clear? Next. In case if there are two double bonds and I'm only sending one equivalent to add, in such case, how do we make a addition? See, here it's very simple. In rings, whenever you talk about ring sizes, if the ring size is greater than 10, if ring size is greater than 10, the stability of trans is more than cis. So naturally, cis is less stable. That means it is more reactive. So I'll write the reactivity order also. Since the stability is like this, then when it comes to reactivity, cis will be more reactive than trans. If cis is more reactive, you can see this side there is cis, this is trans. Because you can see clearly here hydrogen are added here like this. That means it is in a cis form. Hydrogen and hydrogen are here in a trans form. So now the upcoming hydrogen, okay, has to get added. Where does it get added? It will get added on this direction. So everybody, oh, how does the product look like? This is how it would be. Double bond here, and here you will have both the hydrogens getting added. Hydrogen, 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 and hydrogen. Done. Trans would remain stable. Now, if you have carbon less than 10, okay, if you have carbon 10 or less than 10, in both cases, 10 or less than 10, then cis is more stable than trans. This is about stability. If this is the stability, then reactivity wise, if you notice, trans is more reactive than cis. In such case, how does the product looks like? This way. And now you will be adding hydrogen here. Hydrogen and hydrogen getting added. This double bond will remain. Got it? Clear? Please make a note of these examples. If you have any doubt, you can ask me now. Okay, I'll pause for a minute. Let's continue further. If you want to notice what would happen to the rate of hydrogenation, okay, hydrogenation mainly depends upon the steric hindrance. If on across the double bond or a triple bond, you have a huge crowding of alkyl groups, then it becomes difficult for it to adsorb on the metal surface or come close to the metal surface. And it is the metal surface on which hydrogens are embedded. And if those hydrogens has to come out and make a bond with these double bonds and triple bonds, they have to come much closer to the metal. For that, they need to be as smaller in size as possible. That's why sterically, if they are more hindered, the rate of the hydrogenation decreases. And if you may notice, if these are all the molecules which are present, which has double bonds and triple bonds, this triple bond has the least amount of hindrance around it. Then slowly the hindrance is increasing. And these three are triple bonded forms, and triple bonded are linear, so they get more easily adsorbed on the surface of the metal, while double bonded are planar, so they are obviously less attracted, or uh, they will have less amount of adsorption rate as compared to that of a triple bond. Therefore, if you compare the rate of hydrogenation, definitely this would be the highest in rate, then this, and that will continue towards double bond as the steric hindrance keeps increasing. So, highest the steric hindrance, least is the reactivity. Let me put that into a question here. See, there are two double bonds here, one with a larger steric hindrance and one which does not have any steric hindrance, only hydrogens are there. And if I use one equivalent for reaction to take place, that one equivalent will always attach on this position only. So you'll have deuterium and deuterium here, and this double bond will form. This is the product, correct? So it will always choose the double bond which is less substituted or which has less steric hindrance. And for that matter, if you notice this one here, you will see the same thing. If you have a double bond and a triple bond, first preference is always about triple bond to convert into a double bond when you take the first equivalent. Now in the second equivalent, you see that this double bond is less crowded than this one. So if I take the same D2 in the presence of nickel, but with one equivalent, this time the addition will happen on this direction here, on deuterium and deuterium, like this. Okay, this is the addition which will happen. Sorry, here I wrote it like a trans. You know that it is a syn addition. So methyl will be here, deuterium and deuterium, like this. Clear? This is the final product. All good? Next. In case if you have to go through 1,4 addition, what is 1,4 addition exactly? For 1,4 addition to occur, you need to have a double bonds at a conjugated position. These two are a conjugated position. Okay, they have resonance helping each other. Let me put some resonating structures for it. How does the resonating structures look like? You will have a double bond character here with minus and plus. This is one resonating structure. And the same goes the other way around also. Plus and minus, like this. Okay. This helps much more easier for hydrogen to get added. One hydrogen on this end and one hydrogen on this end. Therefore, the major product what you will get is like this. One hydrogen here, and a double bond here. This is major product. And because the hydrogen is getting added on these positions, if you notice 1, 2, 3, 4, 1, 2, 3, 4. Addition happened at 1,4 addition. Sorry, at 1,4 position. Hence, I will call this as the major product, which is 1,4. And then 1,2 addition means hydrogen and hydrogen getting added here. This is 1,2 addition. This is minor. Okay. Let me explain you why that will happen. First, of course, resonance will help getting this polarity on which hydrogens can get added. And if you notice this one, this pi bond, while it is attaching onto this hydrogen, this pi bond will move here, and then this hydrogen will attach here. On doing so, what is happening here is that you will notice a six-membered ring formation here, like this. You can see this is the movement of the pi bonds and new bonds which are forming. And here is hydrogen and hydrogen connected with the metal surface. Okay. So what we are getting here is a six-membered cyclic transition state. Got it? So due to this six-membered cyclic transition state, right, you will see the addition would be favorable at 1,4 addition more than 1,2 addition. So here you'll get hydrogen and hydrogen, and you will always end up getting cis product and not trans product, because you need to make a syn addition here. So it is a syn addition. You'll always end up getting cis product and not a trans product. So you do remember that when it comes to stability wise, okay, six-membered cyclic transition state is more stable than four-membered cyclic transition state. So that's why it is more preferable, and that will give you major product as 1,4 addition rather than 1,2 addition. Clear in this case? Let us put that into this example. I would suggest all of you to write along with me. Check out. In this case, you have a conjugation of these two pi bonds. Hence, we will have a product like this. Double bond here, hydrogen here, and hydrogen here. This is a product. And here also double bond here, hydrogen here, hydrogen here. These are all 1,4 products, you can see. And you have an isolated double bond and a conjugated double bond. Always give preference to conjugated one, because 1,4 addition is more favorable when you add one equivalent. Okay, now listen, this is a very interesting case here. Okay, in this case you cannot make 1,4 addition because that is in a transoid form. You cannot convert that into a cisoid form. This is a transoid conformation. Because this bond is restricted, you cannot bring this bond towards this side. You cannot bring this double bond on this side. Hence, this time it will only go for 1,2 addition. It will not favor 1,4 addition because it cannot make a six-membered ring here. Hence, you will see only hydrogen and hydrogen getting added on this end with a double bond here. Now here in the last case, the reactant which we took is anthracene, and if you get a hydrogen to be added here, double bond is here. Here is where you will add hydrogen, hydrogen, and this is how the double bond will be. So you can see 1,4 addition has happened here. 1,4 addition, and this is the major product. Correct? Yes, all of you are clear? Any doubt? These are all the cases you need to embrace from uh, catalytic addition, everybody. 1,2 addition, 1,4 addition, crowding, when if one equivalent is given, where to add, when you get erythro, when you get trio. These are all the pointers you need to recall in here. Now, let's go to the second reaction in alkanes, which is called Woods coupling reaction. The overall reaction is this: if you take two alkyl halides, where X could be chlorine, bromine, or iodine, and if I take 2 moles of sodium in the presence of ether as a solvent, then you will notice these 2 moles of alkyl will connect with each other and form an alkane here. And sodium, on the other hand, will take the halogens and convert into NaX. The shortcut way of Wood's reaction, whenever you notice that, is like this. You have Rx plus 2 moles of sodium plus XR here, and then you try to you try to remove these groups and connect the rest of the two. And on doing that, we will get this R and R connection plus 2 moles of NaX. This is the shortcut you need to use. There are two types of mechanisms that are suggested. The first mechanism is called radical or non-polar mechanism. This is non-polar mechanism. In the case of non-polar mechanism, what you would see here is that, let me start off with a simple molecule here. Let's say I have an alkyl halide like this, correct? And before reacting onto that alkyl halide, sodium in the presence of sodium solid in the presence of ether will try to provide electrons into the solution, and these electrons will try to attack on the carbon which has delta positive and delta negative here due to electronegativity. And as the electron appears, the halogen will start moving away, thus giving a radical positioning of propyl here and X minus here. Got it? And now this radical, you see this radical with another molecule of the radical, when it reacts with it like this here, then here you will notice uh, this radical can go attack on this position, provide a radical of halogen here. So you will get like this, connected like this here. Okay. So let me point out the carbons which we are connecting. Sorry. The carbons which are connecting are these two, this carbon and this carbon. So these two carbons got connected, and that relieves an X dot, and this X dot will take one more electron which is released from sodium to convert into X minus, thus giving an alkane as the major product. This is called radical mechanism. There is a side product also which can be associated here. The side product includes, that is, if you have this radical, the radical, instead of taking away halogen position, because getting connecting with this carbon will also be challenging because it already has some positive charge. So what it can do, it can take away hydrogen from here, create a radical, and then X dot can go away, create a radical here. So these two radicals will terminate to make a double bond. So remember, this radical will try to connect onto hydrogen, which will split into these radicals like this, and halogen will also split into radicals like this, and thus giving a hydrogen here. Let me point out which hydrogen. This one is the same hydrogen, and that plus here the molecule will get a double bond plus X minus, sorry, X dot. Got it? That's how you can get a double bond here, as well as you can get this product here. Clear, everyone? This is the side reaction which can take place. Usually major product will be alkane unless there is any crowding across the radicals. If there is large crowding, then the connecting between the carbon becomes difficult. So this will become major product. But otherwise, if you don't have a lot of crowding around these carbons, this is alkane formation is the major product. This is a radical way of explaining. Okay. Then there is polar way of explaining also. Sorry, here I have written it radical. Let me put it into the polar form here. Polar mechanism here. So one is non-polar mechanism, the other one is polar mechanism. See, in polar mechanism, you can assume like this, that I started off with 2 moles of sodium, which in solution are becoming 2 Na plus 2 electrons. 2 electrons as a pair, you can imagine, it can act like a strong nucleophile. Now, that can attack on the alkyl halide more easily. So these 2 electrons, as it attacks here, you will end up getting minus charge on a propyl position and X minus. And This propyl minus can again attack on the alkyl halide part here, and as it attacks here, this X minus can be relieved. Okay, and that will give you connection of these two carbons. Again, let me point out which carbons we are talking about. These two carbons are these two carbons here, thus ending up getting an alkane here, and X minus has been removed out, and it does not make much difference here. Now we learned, I mean, we will be learning about the mechanisms regarding elimination, but just for the sake of understanding here, I'll show you what is a side reaction. This molecule, when you react with this X here and hydrogen here, now this can act like a base also. It can extract this hydrogen, push the bond here, and try to remove this X. This type of mechanism is called E2 elimination. We'll be learning in details, don't worry about it. So due to E2 elimination, what you will notice here is you will get a hydrogen at this end, and you will get a double bond plus X minus. These are the side products. So have you noticed that the side products as well as the main product or the major product is exactly same? So that's why both the mechanisms are equally accepted. So polar way of explaining or a non-polar way of explaining leads to the same products. Okay. So what if you have two different alkyl halides? So far, the mechanism and the products are suggested on the basis of same molecule. What if you have two different alkyl halides? So in case of different alkyl halides, first this ethyl chloride can give you and coupling of its own and convert into an butane. So you will get N-butane, which is called self-coupling. Second, you have propane, which can form hexane, which is N-hexane, which is also self-coupling. Next, we can also have a cross coupling where you have two carbons and three carbons connected with each other like this. Five carbons will come across, and then you get this as N-pentane. So this is called cross coupling. So these are the three products that you can form as alkanes. Got it? But which one is major? We can't say. We cannot say that, okay, one is major over the other. Correct? All three are equally probable products. So we can't say one is major over the other. But are these the only products? Have you noticed earlier that when you have propane, correct? When you have propane, you are already getting two side products, which is, sorry, when you have a propyl halide, you were getting, from this propyl halide, you are getting two side products. One is propane, the other one is propene, which means even these two will give you side products as well. So what are the other side products? Let me write down. One is the propane. One is the propane. The other one is propene. Plus one is a butane. The other one is butene, like this. So these four are minor products as well as, side products. Now, this was a JE question which was asked earlier, everybody. Same reactants were given and it was asked, what are the possible products? When you say possible products, that means you're supposed to count all major, minor, everything that is possible. So in that case, you can see 1, 2, 3, 4, 5, 6, 7. So total we have 7 products possible. Total 7 products possible. Clear, everybody? Please do check. If there is any problem in understanding, they can discuss with me, right? See. What are the other similar reactions here? In case, if instead of alkyl halide, we have an aryl halide, that is benzene plus halogen, I mean benzene connected with halogen, this is called halobenzene, right? Or also called as phenyl halide, because that benzene form is read as phenyl when it is a substituent. So it is phenyl halide or halobenzene. When you take two halobenzenes react with sodium in the presence of ether, there also the same termination would happen where X and X is left with sodium and you'll get 2 moles of NaX and the product is biphenyl. Correct? This is the product which is biphenyl. But you do not use the word woods. Woods is dedicated only for alkyl. Now the word that we use is fatigue reaction. This is called fatigue. If one of them is aryl halide, the other one is alkyl halide, then the product what you will get is, alkyl benzene. The product what you get is alkyl benzene. Okay. Similarly, if you have an aryl iodides, this is specifically for iodide. In case of aryl iodide, I'll take 2 moles of copper, correct? Then you will end up getting Cu2I2 and biphenyl. That reaction's name is Ullmann's reaction. And in case if you have an alkyl or aryl, it doesn't matter whether it is alkyl or aryl for both of them, in the presence of zinc and anhydrous HCl, if these two gets connected, R and R gets connected, correct? So then that is called as Frankland's reaction. That is called Frankland's reaction. So it's pretty clear that Wood's reaction have a similarity with the other type, which is fatigue, Wood's fatigue, Ullmann's, and Frankland. Here, everybody, the reaction set is same, but just the names are different. Okay. Now, there have you noticed some concerns regarding these reactions, Wood's reaction or fatigue reaction or so? The main concerns here, the main concerns here is that when you have a cross product, when you have two different alkyl halides, we are not able to generate one product as a major product. You'll get multiple products here, right? And this happens with all these cases. And to get something major of any crossed product like this, correct? In that case, we have another reaction called Corey-Howe synthesis. After almost 60 years of working, 60, not working exactly, after 60 years when the woods has already been inactive, after 60 years, there was an invention by Corey-Howe, which has been called as Corey-Howe synthesis, where instead of taking sodium, he took lithium into picture. So if I take alkyl halide with lithium in the presence of ether, and then add some cupric salt, okay, cuprous salt, and thereafter you can react with any alkyl halide, which generally are 1 degree and 2 degree alkyl halides, then you'll end up getting alkenes. You'll end up getting alkenes. This is what we call it as Corey-Howe synthesis. Okay. Let me show you mechanism with some example here. Let's say I took an propyl halide here like this, and this has been treated with lithium. You know that lithium is excellent provider for electron. They will provide electrons. Lithium batteries, you know that it can provide electrons much easily. So lithium will provide electron here. Okay. And I'm taking 2 moles of lithium just to show the polar side of the mechanism. I told you, right? Polar, non-polar, both side of the mechanism are equally accepted. So the polar mechanism is you take 2 moles of lithium, you will end up getting a minus charge here, minus and lithium plus like this, correct? And another compound is LiX. Now, this if I take 2 times, 2 moles of it, 2 moles of alkyl lithium compound, that when you react with CuX, now I can take X anything beta. It could be chloride or bromide or iodide. Anything will be fine. Now, when you take that, you will get this alkyl group getting connected on it. Okay, one second. Okay. So this alkyl group getting connected on it. So you will get this as the minus part which is there here, correct? That will connect, this carbon will connect onto a coordinate bonding. It will make a coordinate bonding from this end. This carbon will make a coordinate bonding with copper here. like this with 2 moles of it. One second. Go closer. Sorry. So same way, this connects on from two directions here, like this, with two coordinate bonds. And you'll have like this, two alkyl groups getting connected here, and that with plus and sorry, with minus and Li plus, like this. This is a complex formation. So here, generally we write it like this, R2Cu Li, and it is called as Gilman's reagent. Gilman's reagent. It is called Gilman's reagent. Next. Now you have this Gilman's reagent, which is this two times propyl group, two times connected to copper, overall, overall with minus charge and lithium plus charge. Now this Gilman's reagent can be now connected to any alkyl halide, does not make any difference. So let me take this as CH3, CH2Cl. This is a new alkyl halide. In that case, what would happen if I take 2 moles of this? These carbons will attack here, removing this chlorine. So I'll get 2 moles of CH3, CH2 connected with this propyl group. And that plus CuCl will form and LiCl will form. Got it? So what we got is a crossed coupled crossed coupled product, which is major. Otherwise, have you noticed with the woods, the major problem was we were not able to get it as a major product, and that is being resolved using Core synthesis. See, if this alkyl halide which you are taking is not 1 degree or 2 degree or methyl, if it is 3 degree, they end up getting alkenes rather than alkynes. Why would that happen? We will learn it in elimination kind of reactions. But as of now, because we didn't go through it, again, I'll be repeating that uh, same reactions, repeating the same reaction when we study about E2 and E1 type of elimination. But for now, you just remember if you have alkyl halide, it should preferably a 1 degree or 2 degree type of alkyl halide. Correct? And see one more example I'm showing. If you have this case here, the second step would be, CH3 Li reacting with CuX, taking 2 moles, you'll get 2 moles of, sorry, you'll get CH3 twice CuLi plus Lix. This is Gilman's reagent, and that CH3 twice CuLi plus any alkyl halide. Let's say I take this propyl bromide. Propyl bromide, I will get this as N-butane of 2 moles plus CuBr and LiBr. So this is major product. Clear? Like this. Now, if you take this Gilman's reagent, try to react with sorry, halobenzene, vinyl chloride, or a bridge position chloride or a tertiary chloride. In such cases, you will not find any reaction. No reaction here, no reaction here, no reaction here. Here the reaction will take place, but it will end up getting 2 moles of methane plus, alkene here. You will end up getting 2 moles of alkene. This is called E2 elimination. You might ask, sir, why these reactions are not happening? Again, we'll come across this. These are, unfavorable forms for SN2 mechanism. favorable alkyl halides for SN2 mechanism. What is SN2? As we go ahead, we'll come across that. As of now, just as a basic information, you keep it. We'll be learning about all the SN2 reactions where again the same reactions will pop out. Okay. Now, when you have a secondary group, you will definitely get this product from here. This ethyl will get connected. This will 2 moles of that will be major product, and you will have this as CuCl plus LiCl. Okay, and you will also end up getting a minor product which is an alkene group. Okay, this is via A2 mechanism, and this is via SN2 mechanism. Next, if you have sodium and ether here, if you take these two cross products, so you can see this is one important statement that has been asked in exams. So do remember that no odd main chain alkane, that means major product alkane, can be achieved as a major product with Wood's reaction. Does that make sense? Why? I'll tell you. If you take an ethyl chloride plus methyl chloride, do you get propane as a major product? No. Here you can get this one, you can get N-butane, you can get ethane also. All these three products are equally probable. So none of them is one major product. So which means, you know, groups, I'm sorry, products which cannot be achieved, which cannot be achieved as major in Wood's reaction. Wood's reaction. See, in JEE mains, when these questions were asked, they haven't even mentioned all of these lines, that the products which are achieved as major and all of that. Simply, they have mentioned statements like which of the following are not prepared by Wood's reaction. Simple. But the idea behind that, or the underlying statement behind that is this one. Is talking about the major product in that core question. So for the major product ones, which cannot come as a major product here, first one definitely methane. You cannot get methane as a major product. Then you have all three carbons here. Propane, you cannot get. Okay. Pentane, you cannot get like this. Got it? You cannot get this one. Pentane. Uh, 1, 2, 3, 4, 5, 6, 7. You cannot get this 7 carbon as a major product here. You cannot get this part. Next one, important one is, even though you have this compound given, this can form but not as a major product. Okay, now here is an important catch. If the statement is exactly mentioned like this as major product, then you say this cannot be major product because of the crowding reason. Because see what happens here, this radical plus this radical combination to get into this substituted uh, hexane form is very difficult because of the crowding reason. That's why it is minor. Got it? But can we achieve this via Wood's reaction? Answer is yes. We can get this via Wood's reaction. So be very smart in terms of dealing these questions. If in mains, if it's an integer type question and it is only said which of the following can be achieved or which cannot be achieved by Wood's reaction, then this can be achieved. So sorry, this compound can be achieved through Wood's reaction. So don't take it into consideration. But if it is specifically mentioned, especially in JEE advanced question, they always specifically mention this wording that which cannot be obtained as major product. In that case, you have to consider this also because you cannot achieve this as major product. Okay. So these cases are clear, everybody? Yeah. So I hope the second reaction, which is Wood's reaction and Korehouse synthesis, why it is being used, how it is being used, what is the mechanism behind it, what are the cases behind it. I hope all of this part is clear, right? Next, let's go to the next reaction set, which is Kolb's electrolysis. Okay, as a short, we'll use it as KES. Basically, we have to take sodium or potassium carboxylate salts. So you can take first acid and base reaction can be done through which we can get the salt form. So sodium carboxylate salt is observed. And when you perform electrolysis on it, then R and R will get connected and you will get Na2CO3 as a product. Got it? So there are two set of reactions that can happen here. Because you are performing electrolysis, electrolysis is a method where you will take, a cell here in which solution is being fixed. Then you will have two electrodes. One is anode, the other one is cathode. So you will have two set of reactions. One will happen on anode, one will happen on cathode. Got it? At anode, what are the reactions that will take place here? You can see you can have the first reaction here as R, 2 moles of RCOO minus. This will give you 2 moles of RCOO dot as a radical and releases 2 electrons. And you notice that second step is this 2 moles of R C double bond O dot, the radical form is unstable. And this will lead to the formation of, I'll keep it in an equilibrium form because this can come back also. Now, this will become 2 moles of radicals plus carbon dioxide because the bond here will break into a radical form and get 2 moles of radicals and 2 moles of carbon dioxide. And that brings you third reaction, which is R dot plus R dot will combine to form R and R. And that's how you're getting an alkane, everybody. And remember, alkane is actually forming at the anode. Alkane is forming at anode, right? So carbon dioxide is forming as well as alkane is forming here, correct? Now you may have noticed that there is a decrease in the carbon number, right? So therefore, this is also called as step down reaction, step down reaction. And since you are removing out carbon dioxide, it is also called decarboxylation reaction. So if this wording is used, which of the following gives decarboxylation? Kolb's electrolysis is one of them. Now, what's happening at anode? See, you will be taking this in an aqueous solution. That's the important idea you need to remember. So, in aqueous solution, it is the water that itself will try to get reduced on its own. So, therefore, 2 moles of water here. So, 2 moles of water will take the electrons which were released from anode, okay, convert that into H2 gas and release 2 moles of OH minus. Okay. Now, obviously, some part of carbon dioxide might escape, but some part of carbon dioxide can react with this OH minus. And in the overall reaction, if you notice, in the overall reaction, you will write it like this: 2 moles of COO minus Na plus, right? In the aqueous solution form, or let me put it as water for our easy understanding. This aqueous plus H2O, 2 moles of it, will give us, right, R and R plus 2 moles of carbon dioxide with Na plus and hydroxide will convert into Na2CO3 of 2 moles, correct? Na2CO3, 2 moles has formed here. Sorry, here you can see this as CO3, 2 minus plus, sorry, you already got minus 2 moles of OH minus. This OH minus will also have Na plus on it. So 2 moles of Na2CO3 is what you can put it up. Correct? Plus H2 gas. 1 mole of H2 gas. Now notice Na2CO3 is basic in nature, right? This is basic in nature. So since it is basic in nature, what should happen to the pH of the solution, everybody? So important note to understand here is during electrolysis or during KES, pH of the solution increases. pH of the solution increases and solution becomes more basic. Solution becomes more basic. Okay. This is one very, very important form, not just for this topic. You will come across the same reaction, same set again in electrochemistry. So my suggestion is you write and learn. All right. So I'll give you a minute's time. Please go through it and write. Let's work out on all the examples here. First one. If you have 2 moles of propyl propanoic salt, so what do I get? Hexane, butane 1, 2, 3, 4 plus 2 moles of Na2CO3. Next, you can see here, if you have two acidic groups on the same position, you know that first you will get COO my dot here, COO dot here. Both those dots will come out as carbon dioxide, leaving behind dots here. And these two dots will terminate to give alkene here. So which is ethene. So ethene is a major product in this case. See, radicals on the same molecule will terminate there itself. Again, they will not try to make a coupling with the other molecule. Okay. So they will internally terminate. Next. Check out in this case also, you'll get a dot here and a dot here. So you will get a dot like this, dot here and dot here, plus 2 moles of carbon dioxide got released. And these two internally terminate with each other at these two positions here. So 1, 2, 3, 4. So what is the product you will get is cyclobutane. This is a major product. Similarly, here you can notice that again I have dot here with a double bond plus 2 moles of carbon dioxide got released. Now here there are two things that could happen, correct? That means you can see that this dot here and dot here can terminate to get a product like cyclobutene. But due to the strain here, it is very difficult to achieve it as a major product. This is minor product. But another way is that you can break this pi bond into two radicals. And here one radical and one radical here can terminate. Here these two can terminate. And that gives a very stable product, which is, cyclobutadiene. Sorry, butadiene. Correct? Which is stable because of resonance. So this is major product, everybody. Every question, whatever I'm writing, they are all asked in previous years. Please learn it. Okay, anything could come. So these are all the PYQs only. Check. Next, here also CO2 will go away. You will get already existing double bond. On top of that, we have two dots here plus 2 CO2. And those two dots will terminate again. So you will get alkyne here. Next, here you can notice you'll get dot and dot here plus 2 moles of CO2. Again, these two will terminate. You get double bond here. Again, here also. Now, this is very interesting. I can get 3 moles of dot and dot here. But obviously, a triple bonded carbon here on a cyclic structure is very difficult to achieve and also it is unstable. So, what would happen? These 3 moles will terminate with each other. And when these 3 moles will come each other, they will come like this. You have a triple bonded carbon here, like this. You can have a triple bonded carbon like this here. Sorry, yeah, here, like this. Triple bond here, like this. And one more, which is coming from this end, dot and dot. Okay. So these three will terminate with each other like this. This will connect here, this will connect here, this will connect here. So those three connections will lead to the formation of this cyclohexyl type of group here, like this, with double bond, double bond, double bond, which is called as tri trialkyl. All right. Similarly, in case if you have a benzene and you take only 2 moles of it, so if I take 2 moles of it, so first I will get is benzyne form. This dot and dot is nothing but a benzyne form. 2 moles of benzyne intermediate, and benzyne intermediate will terminate here. If you have 2 moles, they will terminate like this, forming a cyclo uh, butyl ring like this. So this is called di di dibenzylene. One second, phenylene. Sorry, diphenylene. These are the product form. So I suppose all the codes cases are clear, everybody. Next. The next type of reaction is called soda lime decarboxylation, also known as Oakwood reaction. So, in case if you have any carboxylate salts which are being treated in an anhydrous condition of 3 is to 1 ratio of NaOH and calcium oxide in a powdered form, you add to it, then you will end up getting alkane and Na2CO3 on heating. How is the reaction going to proceed here? Check it out. When you have NaOH, I mean carboxylic salt in the presence of a fused NaOH form, the first step itself is like this: RC double bond O minus and Na plus. This on strong heating, it will break this bond towards alkyl group here as the oxygen will push here. You will end up getting an alkyl carb anion and carbon dioxide. Of course, this carbon dioxide, if I take 2 moles of this one, it will combine with NaOH of 2 moles to convert into Na2CO3 form. And now this is the rate determining step, which means stability of stability of carb anion decides the rate of reaction. And second step is that now if you have this 2 R minus, it will react with H2O which is released. See, there will be H2O which is released here, and it will catch up with this hydrogen and converts into 2 moles of RH. 2 moles of water here, and that will convert into 2 moles of this and 2 moles of OH minus. So what you are getting is an alkane part. Correct? So here also you notice that this is a step down reaction. Step down reaction. This is also a decarboxylation reaction. Decarboxylation, and most importantly, you need to remember it is about stability of carb anion. So more stable carb anion, better is the reaction. Clear with SLDC? This is about soda lime decarboxylation, everybody. While if you compare all the SLDC rates here, all you need to do is remove the carbon dioxide in all the cases and check out which one is more stable carb anion. Okay, on that view, let me show you. If it is about the first case, the carb anion will be CH3, CH2 minus. Here it is CH2 double bond CH minus. Here it is CH triple bond C minus. So what are we having? These are the carb anions we have. And you know that rate of the reaction will be A less than B less than C, because the triple bonded carbon will have more stability as a anion compared to that of single bonded carbon. Next, if you have any groups here at para position, and then you have a carboxylate form here, you remove this carbon dioxide, you'll get a minus charge here, so this will become benzyl form. So now on a benzyl form, if we compare the rate here, so you would have that as uh, on this carb anion, what do we have based on? See, carb anion stability depends upon how strong the withdrawing group is. Electron withdrawing groups will make it stronger or more stable carb anion. So in that case, NO2 is strongly withdrawing, then chlorine is withdrawing, then nothing, no effect is on hydrogen, then A is donating, B is highly donating. So this will be the rate of reaction. So stability, electron withdrawing groups are more, that means stability, carb anion stability increases. Electron donating groups are more, carb anion stability decreases. So this is the case you need to follow in this. Third case, if you have here observing these two cases, you can see what is the carb anions we can get here. One carb anion is like this. The carb anion is this one. So you can see between A and B, the B is aromatic. This is anti-aromatic. So rate would be B greater than A. Okay. Next. Here out of these three, you can get carb anion on a benzene itself, which is stable. Phenyl is stable, correct? But CH2 minus is more stable because it has a resonance effect also. And on sp carbon, the stability will be less. Therefore, rate wise, B is more than A than C. The first type of question from SLDC will be all about rates. So remember, you have to just check out carb anion stabilities here. Next, what are the products? You can see quickly we can write the products in these examples as well. So in the first case, the product is just try to remove the carbon dioxide and push this hydrogen with it. So what do I get? PHH, which is benzene. Second one, RH with Na2SO4. Alright, in this case, because we have sulfate. Next, this is important. You can get a carb anion here, which can show resonance stabilization like this, which means after reacting with the water here, you will get two products, one with hydrogen here, one with hydrogen here. And if you notice that this is the isotopic carbon we are talking about, correct? So that means I get two products here. Both of them are allyl forms, and chances of these two are 50-50 percentage. So 50% of this product and 50% of this product. This is what you need to represent. Second, in this case, you notice that first you will get a minus charge here. Chlorine is present. Where the carbon dioxide is going, that is the alpha position. Adjacent is beta position. At alpha position, if you have minus charge, that minus charge can be pushed to make a double bond and remove chlorine. So instead of getting an alkane, I will end up getting alkene. Same way, if you have OH here and you will get a minus charge here, here also, even though OH is a bad leaving group, it can still be relieved out and you'll always end up getting alkene. And if you have it internally like this, you have Br here and then minus charge is forming here. Again, internally it can attack and remove Br, and you'll end up getting cyclopropane. This is the major product. Got it? So remember these special cases, D and E. You know what are the products you can get in SLDC. Everyone clear? Next. See the next set of reaction. To get the alkanes, we can use very important reagent known as Grignard's reagent. Okay. The representation of Grignard's reagent is RMgX. X could be chlorine, bromine, or iodine. If you take Rx, react with magnesium, in the presence of ether, you will break this bond here because magnesium will provide two electrons. And those electrons will connect on to alkyl group, convert into R minus and MgX plus. And here R minus, I mean, although it is a covalent compound, correct? But there is very high charge on R and MgX. So this is going to be, in the case of RMgX, you will have very high delta negative, very high delta positive charge here. Since it is a bond between carbon and a metal, so these are called, you know, organo metallic compounds. This is organometallic compounds. So if you take RMgX and react that with water, so obviously we'll get this as RH, because this is a very high, I mean, there's a very strong base. R minus is a very strong base. It can pull off H plus from any slightly polarized hydrogen. You require slightly polarized hydrogen and it can pull off that hydrogen. So from water, it can easily pull off that hydrogen. From alcohols, it can pull off. From ammonia, it can pull off RH. You can get this as RH. From acids, it can pull off. It can get RH. What is this side product we have? Mg, Mg, X and OH. Here we will have Mg, X and OR dash plus Mg, X and NH2 plus Mg, X and OCOR dash. These are all the products you can get. Correct? Another locations where Grignards can pull off hydrogens is this. One is this one, because here, if I remove the hydrogen, you get a negative charge and the ring will become aromatic. And if you recall, when we learned about various pK values in GOC, this was coming around 16, which is sufficiently acidic. So it can be easily removed. In fact, the pK of this one is around 9. So that is also very strongly acidic, because removing this hydrogen, you get a negative charge and it can make a resonance stabilization on both sides. Triple bonded carbon, although the pK value is around 25, still this hydrogen is highly, is sufficiently positive charge to be pulled off by Grignard's reagent. Double bonded carbon cannot be pulled off. So here you cannot notice any product getting formed. And phenol, the pK value is around 10, so definitely easy to pull off this one. It can be easily pulled off. And on benzene also, if you want to pull it off, it is very difficult, so this cannot be done. And on toluene also, if you want to pull off, it is difficult, it cannot be done. So if this is an integer type question, typically this is how you will be framed. Water, alcohol, ammonia, acid, cyclopentadienyl, okay, diketones, alkynes, alkenes, phenols, benzene, toluene, all will be given. You need to figure out in which case Grignard's reagent will give alkanes. Okay, very, very, very standard JE question. So please check it out. If there is any problem, you can ask me now. Let's go on to the next one. In case if you have red phosphorus and I can call this as the, highest regards as the powerful reducing agent. Got it? Why? See, Hi has a very weak bond. Slightly on heating, the vapors can convert into H2 and I2. Got it? And it is this I2 which reacts with red phosphorus to convert into PI3. Okay, and this PI3 as it forms, right? It can release sufficient number of electrons here like this. And those electrons can be combined with hydrogen to provide sufficient number of nascent hydrogens. Okay, like this H2, if you react with two electrons here, it can convert into 2 moles of nascent hydrogens, radicals basically. See, if a radical is in a solution, you call it as nascent hydrogen. That's it. The same hydrogen radical, if it is in a gaseous medium, you call it as radical. If it is in an aqueous solution, you call it as nascent hydrogen. So it can be giving this nascent hydrogen. Okay, and notice that this pi3, when it forms with h2o, again it regenerates hi, so there is rich amount of hi that will keep on producing. Yeah. So because of this hi, what would happen? Let's say if at all I react with alcohols, right? So you always notice that hydrogen gets distributed like this. You have it, this bond will break here, and you'll get RH and H. So what do I get? I'll get this as RH plus H2O. That is the product you will get. Similarly, so notice how many moles of hydrogen were used. I mean, how many nascent hydrogens were used? Two. So two nascent hydrogens means I'll require 2 moles of Hi. Okay. So that is the information I'll write down here. So we'll be utilizing 2 moles of Hi. Next, if you have with aldehydes, you notice that first bond breaking will happen where you will get this as OH and H and R. So basically, first you will make 2 moles to convert into alcohol. Again, from alcohol, again you will get this as CH2 and R plus H2. So total you will get 4 moles of 4 moles of Hi. Next, if you have nitriles, in case if you have nitriles, I'll get this as R CH double bond NH. Again 2 moles. One more time it will reduce. You will get this as CH2 NH2. Nitrogen will not be lost out of it. So again you will be using 4 moles of Hi. And this is the product you will report. If it is acids, in case of acids, first you see C double bond O, OH is there. So first you'll break this bond, you will get H and H. Okay. So the first thing you will end up getting an aldehyde, RC double bond OH. And again you will put one H and H here to convert that into an alcohol, RCH2OH. Again you will break this bond, give H and H, and you will end up getting this as RCH3. So total how many moles are used here? 6 moles. 6 moles of Hi are used for acid to be converted like this. Next we have again aldehyde. You can see 4 moles of Hi. I'm directly writing the product. You will get this as RCH3. Okay. So I hope all of you got this point. How many moles are in used, and it can reduce literally all functional groups to almost alkanes and amines. So this is a typical question given. If you have glucose with red phosphorus, what do we get? See, 1, 2, 3, 4, 5, 6. 6 carbons we have. So what we get here is N-hexane. We'll get this as N-hexane. And how many moles are being used, everybody? Check out how many alcohols we have. 1, 2, 3, 4, 5. 5 twos are 10. And 10 plus another 2 here. So total 12. So 12 moles of Hi will be used in this case. JE question. How many moles of Hi are used in the case of glucose to convert into N-hexane? Red phosphorus Hi is clear, everybody. It's not that difficult. It's just pushing all the hydrogens here. Next. Another reduction form which can be reducing into alkanes is Clemenson's reduction. Basically, here the reduction is for here the reduction is for aldehydes and ketones. See, if you have an aldehydes and ketones, that C double bond O group can be converted into CH2 using zinc mercury amalgam. The logic is same. Zinc, as it dissolves in HCl, will release nascent hydrogens, and that nascent hydrogens will come on this carbon position to get H and H. Okay. So during this nascent hydrogen formation, everybody, if you have Cl here, correct? This group anyway is converting into H and H. But if you have sufficient excess amount, even the chlorides can be removed out in acidic medium. So again, you will get H and H here, H and H here. So alkane should be the major product in case if excess is given. Otherwise, you will end up here. So similarly, here you can see aldehyde is there. So the product should be CH3. Ketone is there. So the product should be D and D because it is DCl. And if you have chlorines here, so you can have this as alkane, hydrogen and hydrogen with chlorine and chlorine intact. But if you have excess, you will remove even that also and write everything in terms of hydrogen. So you can see H and H here, H and H here. So this is all the Clemenson's reduction part. All right. Mechanism and its uses and very special cases, these are all something which we will learn in aldehydes and ketones. While solving, while solving the MS Chauhan, you will also find something like nitro groups present in it. Okay. So by chance, where there is nitro group, even nitro get reduced to NH2. Just take care of that part if there is nitro group also. Nitro, for that matter, nitroso also. That means NO also is there with Clemenson's reduction. You will get this as RNH2. Next, Wolff-Kishner reduction. The reagent basically is a hydrazine. NH2 is called hydrazine. Okay, hydrazine. Hydrazine in alcoholic KOH is what we call it as Wolff-Kishner reduction. As it reacts, this C double bond O will convert into CH2. Okay, so here, while you get on this position, you will have Cl, and this is very interesting to notice that in Wolff-Kishner, before getting an alkene, you will get a carb anion. And if you get a carb anion, this can push here, remove this chlorine and convert into an alkene position. See the slight difference between Wolff-Kishner and Clemenson's. This product is the same. Here you will get CH3, there is no problem. Here also you will get both hydrogens, no problem. The role is same. But here you can see when you have like this, reduction will happen on this position. But chlorine from here will go away, double bond will come at this position, or double bond will come at this position. You'll get obviously an alternative double bond which is more stable form. So first let me write down the chlorines, sorry, and I can write it in the excess form. So first chlorine will be here, and if the Wolff-Kishner reduction is in excess, so you will have to make an conjugative double bonds here. In both forms, you can make it on either side. This is the product you will get. So these are the important cases you need to learn from Wolff-Kishner reduction. Next is with lithium aluminum hydride and NaBH4. These two are very, very powerful reducing agents. They will provide H minus ions in the solution, not nascent hydrogens, but H minus. So that H minus can replace the halogens to convert into alkanes. So by chance, since lithium aluminum hydride is very strongly pushing H minus, its H minus is very, very reactive. So the reactive would be more for methyl group compared to 1 degree compared to 2 degree, and not for 3 degree, for not for 3 degree alkyl halides. While in case if you notice sodium boron hydride, it will typically take an SN1 route. SN1 route means first carbocation will form and then H minus will attack. So in that case, the reactivity is more for 3 degree, then 2 degree, and for 1 degree and methyl, here there is no reaction that will take place. For these two, there is no reaction. Okay. Then there is a special reagent here, which is if you have a tertiary alkyl halide, triphenyl tin hydride. It's a very special industrial reagent which can provide H minus on a tertiary position. But first, it will make it a carbocation and then H minus will attach onto it. So here the rate will be very high in the case of 3 degree, 2 degree, 1 degree and methyl. That means it will react in all the cases, everybody. It is not just for 3 degree. It can be 2 degree, 1 degree methyl, but the react rate will be more for 3 degree. Correct? So have a quick look of Li, ALH4, NaBH4. By the way, this is all the statements directly mentioned in NCRT as well. So you can go through it out. Next. Notice sodium in ethanol. Sodium is ethanol is also provider of nascent hydrogens. So that can release this, remove this hydrogen, halogen and make it into similar reaction as LiAlH4. So let me write on that. Similar to LAH reaction. Zinc in acid, zinc in alcohol, zinc in methanol, all of them will give the same reaction. They can remove the halogens and convert into alkanes. Okay. Zinc is an excellent provider for nascent hydrogens. That's why they can do these reactions. Next, carbides. In the case of carbides, you can see uh, carbons specifically, when you react with H2 in an electrical spark, that is a graphite form, will convert first into acetylene. Got it? If you have CaC2 and you react with water, see CaC2 structure is like this. Calcium is ionically bonded with C triple bond C. On hydration, this H and H will come here. And if you have Al4C3, it will convert into 3 moles of methane. And Mg2C3 will have these two structures form, and this is a major product. So basically, you're getting these alkynes and alkanes. Okay. So if you are getting an alkynes, right? Sorry, if you're getting ethyne, okay, ethanides. So then you will call CaC2 as ethanides. And in case if you get methane, we call it as methanides, Al4C3 or B2C. Both of them will give you methanides. Correct? This one, lithium 2C2. Even this will be ethanides. Then we have allyl allyl, which is Mg2C3. Correct? So remember these words, ethanides, methanides, and allylides. Allylides means you can get, this allyl form or an uh, triple bonded propyne group. This is the product which you will get. Clear? So these are the 11 reactions which are there as the preparations of alkanes, everybody. Got it? These are all the preparations of alkanes. Okay. Next is all about questions, correct? This part is what something which I'll explain as a starting part of alkenes also. I have written the same notes there, correct? Now, my request is you would be first, you will complete these PYQs, correct? This is the first assignment. I would suggest you to try it out. So in the next class, this is the first thing I will discuss. All these questions we'll be discussing. And based on this PYQs, you can now once you finish this part, you can complete. There are very less number of questions in MS Chauhan as much as alkenes is concerned. So you can complete that part there, and you can give a closure to alkenes. Got it? Alkenes is a relatively bigger topic, but it will cover a lot of mechanisms. Okay. So because once you learn alkenes thoroughly, then alkyl halides, alcohols, that will become much easier and we can go very fast. Right. Everyone, any doubts here?